Welcome back, and we will start the next session. The next session is on solar interior atmosphere, about the physics of sun in general, sun and its astrophysics, the solar interior. And we have for this session Dr. Ajor Maurya. Maurya. So Dr. Ajor Maurya obtained his MSc in physics from Deen Dayal Upadhyaya Gorakhpur University, Gorakhpur, and received his PhD degree in solar astrophysics from Physical Research Laboratory, Ahmedabad. After he pursued postdoctoral research on seismology of active regions in PRL, postdoctoral researcher on chromospheric dynamic in Seoul National University, South Korea, and visiting researcher at the University of Sheffield, UK, before joining National Institute of Technology at Calicut. Currently, he is working as an assistant professor in the Department of Physics at NIT Calicut. He is also a visiting associate in the Inter-University Center of Astronomy and Astrophysics, IUCA. He is also a member of astronomical communities such as Astronomical Society of India and International Astronomical Union and Astronomical Society, American Astronomical Society. His research interest includes heliosmology, magnetic hydrodynamics, waves in solar atmosphere, that is MHD waves in solar atmosphere, solar eruptions and associated phenomena, atmospheric heating. He has published over 20 research papers in peer-reviewed international journal and a monograph in solar physics. Currently, he is working on a research project titled Investigation of Solar Eruptions Using Subphotosphere Dynamics, funded by Indian Space Research Organization. So, I would request Dr. Ajor Maurya to kind of present his presentation.
Hello.
Yeah, visible. It is visible. Slide is visible and you're audible also.
Okay, thank you, sir.
You can continue.
Thanks for your kind words for my introduction, and thank you, the organizer, for inviting me to give a talk in this forum about my research works. Okay, so the topic of my presentation is the solar interior and the atmosphere. Here is the outline of my presentation. So we will start with very basics about the sun, that is our nearest star, and why we study the sun and how we study. Then the surface, its interior and atmosphere, how one can observe or how one can do theoretical modeling to understand its phenomenon, and its a relation with the earth. So from the morning and evening, I mean, we see the sun is rising in the morning and setting in the west. Yeah, rising in the east and setting in the west. So how it is. So we are curious to know more about the sun. What are the activities related with it, and what are the interior of the sun, and how uh, it is related with the other stars in our galaxy. So since this is close to us, so if we know more about the sun, then we can understand more about the universe. So that's why it is also called the Rosetta Stone of the astronomy. Uh, so we can ask some questions, very simple questions. If I consider you as a amateur astronomer, for example, how far is the sun from the earth? So you know this is around 150 million kilometer away from us, and light takes 8 minutes 20 seconds to reach us from the surface of the sun. And if you want to find the distance, how far is the sun from us, so we can do some simple calculations by considering another inferior planet. For example, suppose here we have Venus, and this is the sun, and here we are on the earth. So this position, when the Venus would be at a maximum separation from the sun, that is called the greatest elongation position. So we can have eastward and westward. So maximum this angle is 46 degrees for Venus. And using a radar experiment, we can find the distance between the Venus and the Earth. So we know this distance, and this distance, this is the angular distance we can find. So using these two, and then using simple trigonometry, we can find this distance, the distance between Sun and Earth. That is called 1 astronomical unit. So you will find that if this distance is a cosine alpha, that is the distance between this the Venus and Earth, you know, then based on that you can find the actual distance. And from here some other inferences we can find. For example, this distance, if you consider a as 1, then this will come as 0.69, that is 69% of the distance between Sun and Earth. And the distance between the Venus and Sun, that is around 0.72 percent of the distance between the Sun and Earth. We can also use the Kepler's law, Kepler's laws of the planetary motion, to find the distances in our solar system. Another method we can use, that is called the Parallax Method, to find the Sun-Earth distance. So here we have a transit of the Venus from on the solar surface. This in the background we have the Sun, and then we can see the Venus is transiting. So if you observe this event from two different places on the Earth, separated by some distance, let us say one we are observing from let us say from Moscow, and one from Delhi, and then you know the distance between Moscow and Delhi, and then the path of the Sun at when you observe from two different places, it would be different. And then using this you can find the distance between Sun and Earth. I'm not going to tell you detail about it, so you can explore it. So this is called the Parallax Method, to find the distance between the Sun and the Earth. Okay, so then we can ask, how big is the Sun? Okay, this may be another question, simple question. So the Sun is so big. Okay, so if you consider this hemisphere yellow color, that is our Sun. So all the planets, you can see their dimensions. So here we have Jupiter, okay, Earth, then Saturn. Okay, so you can see the size of the Earth. So the Sun is around 108 times larger than our Earth. And this is the diameter of the Sun. This is 1.4 million kilometer. Its radius is 696 megameter. Then why do solar eclipses happen? This we know, it's very simple. Okay. But the solar eclipse, from the solar eclipse observations, we can derive a lot of information about the solar atmosphere. So that way, this is interesting. So what are the there may be some more questions from a solar astronomer. Okay, for example, about the surface of the sun, we can ask, how does the sun's surface look like? Does the sun have a solid surface? Does the sun rotate? Is there magnetic field on the sun like the earth? What are the sunspots? Why do they appear? In the previous pictures you have seen there are some dark patches on the surface of the sun. They are called the sunspots. So these are some basic questions about the sun's surface. Then about its interior also, we may be curious to know uh, how does the sun shine and what is the source of this sun's energy. Does the sun have solid and liquid interior like the earth? How is the internal structure of the sun, and how do astronomers measure the properties of the sun's interior? Okay. Then about its atmosphere, since the sun is so bright, how is it possible to see its dim outer atmosphere? Okay. What are the causes of the eruption in the sun's atmosphere? We sometime in the solar atmosphere we observe eruptions. They are called flares, or you can have coronal mass ejections. These are some energetic activities that we see in the solar atmosphere. So why they happen? Where does the solar wind come from? We have solar wind from the sun. So that is consisted of the energetic particles. There we have electrons, neutrons. What are auroras? Okay, so and some general questions. Uh, Maybe some of these you will know from Ganguly sir's talk. For example, position of the sun in the Milky Way, and how old the sun is, how long it will last, and how will the sun evolve with time. Okay, so these are very basic questions one can ask about the sun, and one may be interested to know about the sun. So some of these questions I will try to answer here in this my presentation. So why study the sun? Okay, um, if you are interested in the previous questions, so that motivate you to study the sun. Okay, the other answer may be, my answer would be, it is interesting. It is interesting to me why you study the sun. Okay, this is a simple answer for uh, the source. This is the sun. We can go some technical also to answer it. So it is source of energy uh, for the earth. Okay, the ultimate source of the energy is the sun. Okay, this can damage the activities from the sun. They can damage our power system. Okay, this can affect our communication system. The sun influences the earth and its atmosphere. So that's why we have the aurora borealis in the polar region of the earth. Okay. Uh, the energetics from the sun can harm our astronaut who are in the space. They can the activity, solar energetic activity, can damage our space stations that we have in the space. Okay, so that's why we should study the sun. The sun also provides us a laboratory for the plasma physics, and this helps us to understand other stars and their activities. Since the sun is very close to us compared to the other star, uh, so we can observe a detailed feature in the solar surface and its atmosphere. That is not possible for other stars because they are so far from us. So we observe them as a point-like objects only. We cannot see the surface feature. Spatial resolution is not possible. But in case of sun, it is possible because this is closer to us. So there are many basic properties still unknown. Still, we do not know about the sun. Okay. So we should try to understand that, we try to give some answer, try to find the solution for the mystery about the sun. So the solar physics is this, this has a relation with other fields in the physics. Okay. Uh, from the solar physics is related with the fundamental physics, the neutrino physics, the gravitations, uh, the sun-earth relation, the climate, the space weather, uh, the cool stars activities, the structure and evolution, the planets and extrasolar planets, the cosmic rays, local interstellar medium, uh, the turbulence dynamics, plasma physics, atomic and molecular physics. All these fields, they are related with the solar physics, physics of the sun. So that's why we should study the sun. Okay. Then how we study the sun? We can study it using observations. We have telescope, we observe the sun, and theoretical modeling, and using numerical simulations. Okay. So we observe the sun in different wavelengths. Different wavelengths give us access of the sun's different layers, different atmospheric layers of the sun. We analyze and interpret the results obtained from the observations. We can also develop theoretical model to explain whatever we observe using telescope, and using computer we can simulate the phenomenon associated with the sun. So this way we can study the sun using observations, theory, and numerical simulations. Okay. Uh, Now let us go to some physical parameters. For example, if you ask how hot is the sun, okay, so we can find the solar temperature from the classical physics. You know the various theorem. So the various theorem says that the total energy uh, can be expressed as half of the potential energy. So this we can prove just by taking, if you take the sun and just take a star and it's a planet, and then you can prove it. Not going to give the proof, it's simple. We are going to use the various theorem to find the temperature of the sun. So the total energy, we have the thermal energy plus gravitational energy. Okay. Uh, and this can be expressed as half of the gravitational potential energy. Potential energy I am replacing by gravitational potential energy. And then in the left hand side we have the full gravitational potential energy. This I'm going to take to the right hand side. Okay. Then it would be half gravitational potential energy, and the thermal energy we can write n into 3 by half kT. Let us say there are n number of the particles, and this is the energy associated with one particle, and this is the gravitational potential energy. Then from this we can get the temperature T as capital Gm square 3 kb n into r, and then you can plug in all the parameters. G is the gravitational constant, m is the mass of the sun, kb is the Boltzmann constant, n is the number of particles, and r is the solar radius. So from this we can estimate the temperature, and it is 10 to the power 6 Kelvin. This was first worked out by Eddington. This way the temperature of the sun, how hot the sun is. Okay. So this temperature we have in the interior of the sun. We have million degree Kelvin, and surface is around 6,000 Kelvin. So this is almost equal to the accurate temperature almost equal to the accurate temperature that we have uh, in case of the sun. So here we have some physical parameters you may be interested. For example, mass of the sun is 1.98 into 10 power 30 kilogram. This is 3.33 into 10 power 5 mass of the Earth. The radius of the sun is 696 megameter. Here we have luminosity 10 to the power 26 arc per second, um, and this is the angular diameter of the sun. It this it means when we observe the sun, let us say two opposite edges, this and this is. Then it will make an angle, means half a degree, around half a degree on our eyes. Okay, that is called the angular diameter. The rotation period, it is 25 days here. This is the equator, and if you go towards the polar region, it is 35, around 35 days. So it's not like a solid body. It's a differential rotation. Sun rotate differentially. Why it's possible? Because it is made of plasma. It's not like a rock solid body. The Earth is. The mean density here 1408 kilogram per meter cube. The distance from the Earth is here. This we have already seen. This is the time taken by the light to come from the sun to us. The surface temperature, and it's a chemical composition is 74% hydrogen, 25% helium, 1% other elements are there, heavy elements. And distance from the center of the galaxy, this is 26,000 light year. Means, you know, one light year is the distance traveled by light in 1 year. So the sun is at a distance of 26,000 light year. It means the light will take this much year, 26,000 year, to come from the center to us. Okay. And here we have its orbital period around the center of the galaxy, and the orbital speed 220 kilometer per second. So very fast it is going around the center of the galaxy. So these are some parameters related to the sun. Then what about its interior and atmosphere? In order to understand it, we have divided into different layers. We have interior. This is called the core of the sun, where we have the nuclear reaction that is producing the energy. Then after that, the energy propagate outward in terms of radiation. You know, there are three modes of the transfer of the energy: radiation, convection, okay, and conduction. So so in this region, the energy is propagating in terms of the radiation. Then after that, there is a convection inside the sun, and then after that we have the surface, that is called this is called the surface of the sun. It is also called the photosphere. And then above that we have the chromosphere, and then outer atmosphere is the corona. Okay, so this is the interior we have, and then the surface, and then we have the atmosphere. So we'll see one by one some detail. So in the interior, so the interior extend from center to about 0.2 to 0.25 of the solar radii. Okay. So 20% to 25% is the core, okay, where we have the nuclear reactors, and the density is 150 gram per centimeter cube. That is, if you compare with the water, it is 150 times the density of the water. The temperature is 15 million Kelvin. Okay, it's a chemical compositions we have here. And if you want to find the amount of energy that is produced by the sun, so it is it is 3.9 into 10 power 26 uh, ergo per second. Okay. And what is the source of this? This is the nuclear fusion. And uh, the Einstein equation, delta E equal to delta mc square. So in the solar core, four hydrogens, they combine and produce one helium. Okay. And along with that, we have some particles, neutrino, and energy. So if you find the mass difference from the four hydrogen and helium, so then you will get the delta m, and then this multiply with the speed of light, then square it, then you will get the energy, how much energy we will have from one reaction. So then based on this, you can find how much uh, the hydrogen is being converted into helium every second. Okay, so this is the luminosity, 3.9 to the power 26 per second. So this much energy is being produced
Good
every
morning.
second, and we can find the energy from this, how one reaction, how much uh, energy we'll get. Then based on that, we can find total mass, total hydrogen that is being converted to helium every second. So it would come around 700 million ton. 700 million tons of hydrogens are converted to 695 million tons of helium. Okay, so then there would be a mass difference of 5 million ton. Okay. And that is being converted into the energy. This is just one animation from the core, then how the energy is propagating, so radiation, and then we have convection, then here we have the photosphere. uh, the interior is opaque, we cannot see. Okay, so we can do theoretical modeling to find the physical parameters. For example, here we have the continuity equations. The rho is the density, okay, and v is the velocity, and this is the equation of motion, uh, and the Poisson equation. This is relation between the gravitational potential and the gravity, and the heat exchange equations. So using these equations, we can model the interior. Okay. And this is a numerical solution of these equations, and you can see the temperature, density, pressure, sound, speed, okay, and metallicity, all these parameters. So the temperature, you can see here, x-axis we have the distance from the center of the sun, 0, and 1 correspond to the surface of the sun. So the temperature, it decreases from the core to outward like this. And close to the surface here, in this part, you can see it is decreasing and then again increasing. So this is called the temperature minimum region. Here the temperature is around 4500 Kelvin, and again after that it increases. And when you go in the atmosphere, for example coronal height, then temperature is again million degree Kelvin. So this is still a mystery. We do not know exactly what are the physics behind it, why we have the atmospheric heating. Okay. Then we have the density, the pressure, and sound speed. All these parameters we can compute from the theoretical, from this, by solving these equations numerically. So so that is the interior. Then we have the surface, photosphere. So you can see this is the surface of the sun, and on that we have some dark patches. They are called the sunspot. The surface, this is called the photosphere. Photosphere means it is the sphere of photons. Okay, that's why it is its name as like this, photosphere. It is sphere of photons. That is photosphere. And here the center, you can see it is brighter. Okay, if you see toward the center, but the limb part, this is the limb. So limb part, you can see it is dimmer than the center. Okay, why is that? That is because when we see towards the center, we are observing uh, deeper, and when we observe towards the limb, then we are observing higher in the atmosphere. And you know the temperature from the surface inward, the temperature increases. Okay, so that's why the limb looks dimmer than the center. The sunspots observations, they they're- they have been observed. The sunspots have been observed from the ancient time, and this is some history about it. The Babylonians were keeping record of the solar eclipse with the oldest record. This is about eclipse, and also they were having uh, the record of the sunspots observations. The sunspots, if you zoom this part, you will find that uh, some detail about it like this. So here, the central dark part, this is called the umbra, and the outer part, this is called the penumbra. And also along with this, you can see some features here. They are called the granules. They are manifestations of the convection that is happening uh, in the sun. So through the convection, we have the energy being transported from the radiation zone and then coming to the surface. So why sunspots are dark? This we can understand from this simple diagram. Uh, Assume that this is the surface here. Okay, here we have sunspots. So the sunspots, they are there we have the intense magnetic fields. Magnetic field is strong compared to the other places, and you know the below this we are having the convection. So what happened uh, in the sunspot region, because of the strong magnetic fields, the convection is suppressed. So energy is not means this transportation of the energy, the rate of transportation of the energy in the sunspot region is less compared to other region. So that's why uh, in the sunspot we see it's a darker, because that region is relatively cooler. Okay, it's not very much cool, but relatively it is cooler. That's why they looks dark. So here we have on the left side, this is white light image. There is some artificial yellow color, and right side we have magnetogram. The magnetogram, this represents the magnetic field on the surface of the sun. Uh, this we can compute using the Zeeman effect. You know the Zeeman effect probably. So we have a spectral line, and if there is a magnetic field, then the spectral line is splitted. Okay, so using that splitting, we can find the magnetic field. So if each and every point on the surface, visible surface of the sun, if you find the magnetic field and then make a image of that, then you will have the magnetogram. This is the magnetogram. So on the surface of the sun, we have the magnetic field around a Gauss. Okay, and compared to the Earth, so you know it is zero point 0.6 Gauss. So larger magnetic field, large amount of magnetic field we have here. But in the sunspot region where we have the sunspots, their magnetic field uh, can go very high, around 4,000 Gauss. Okay, very intense magnetic field we have, and this is you can see some field line, magnetic field line. This from extrapolation, that is called the magnetic field extrapolation. Using the photospheric magnetic field, we can, using some theoretical modeling, we can extrapolate the field. Okay, so you can find the magnetic field in the atmosphere, but directly observing the magnetic field in the atmosphere, it is challenging uh, because of the small amount of splitting uh, in the Riemann effect. And in this you see some dark patches and bright patches. So the dark and bright patches, they represent different polarity of the magnetic field, like we have north pole, south pole. So uh, in case of the sun, we represent that with the negative and positive magnetic field. So uh, that's why these regions, some regions they are bright, some regions they are dark. The sun rotates differentially. So if you observe the sun in white light, you can see the sunspots. They are moving here, right? So you can track the sunspots as function of time at a different latitude. You can track them. Then you can find how the sunspots they are, how the sun is rotating at different latitudes. Okay, so this is the equator. Around equator we have 20. The rotation is 25 days. 25 days. The sun completes one rotation, uh, and at some higher latitude it is 26 days, and if you go towards the polar region it is 35 days. So it rotates differentially. So rotation is not uh, not a like a black like a earth rotation. So our earth is spin in one day completely. The sun rotates in 25 days on the equator. And the sunspots, uh, the their number, uh, if you count the number and plot as function of times, you will find that the sunspots, they show some kind of cyclic variation on the surface of the sun. So that is called the sunspot cycle or solar cycle. Okay. The period of this cycle is 11 years. So after every 11 years, the number of sunspots changes on the surface of the sun. So here we have some observations of some plots of the sunspots. On the top, you can see the x-axis is the time, and y-axis is the, here we have the latitude, minus 90 degrees south to plus 90 degree north. Okay. So if you plot the sunspots positions as function of time, so you will find like a butterfly. This is called a butterfly diagram. And in the beginning, we see there are some features. In the beginning, we see the sunspots. They appear at a larger latitude. Okay, you can see in the north and south. And then after that, it is they are appearing close to the equator. This is the equator. And here we have the number, just number of the sunspots. Okay. So the present solar cycle is 25th solar cycle that begins somewhere in December 2019, and it will end by 2030. So this is the interior, and then so how to model, how to study the interior, how to observe the interior. So one option you have, you can do theoretical modeling to find the physical parameters. The other option is the like studying the interior of the earth using the earthquake. Okay. So we study the oscillations on the surface of the sun, and using that oscillations, using those oscillations, we can find the interior of the earth. So here I think there is some problem. It's running now. So you can see the the up down motion on the surface of the sun. Okay, the up down motions, they are Doppler shift. So you know, if there is a light source coming towards you, or if it is going away from you, then there would be a shift in the wavelength. Okay. Using that shift, let us say shift is delta lambda, so we can find the speed, how, what is the speed of uh, that light source, so that we can write delta lambda by lambda into c, then you can find the speed. So this way, at each and every point on the surface of the sun, you can find the speed, how the plasma is going up and down. Okay, because they are the source, light source. Then we can make it an image, that is, this image is called the Dopplergram. And then this we can have as function of time. For different time we can observe the Dopplergrams and you can plot it. So you will find this kind of features here. Okay. You can see there are up down motions. Why we have that up down motion, that let us try to understand. uh, Here we have the surface of the sun. Okay. And inside the sun, we have learned that there is a uh, the convection we have, radiation there we have. So we can have excitation of the waves. Okay, the acoustic waves, the sound waves. Okay. So when a sound wave is generated inside the sun, and let us say it is propagating, so this is one wave, let us say, and you can draw the wave front. Okay. So this is perpendicular to this the wave direction. So this part of the wave front, so the inner part and this outer part. Okay, so inner part of the wave front, this is facing higher temperature, right? So in higher temperature, because in the interior we have the large temperature, so compared to the sun surface, so this part would be moving faster compared to this part. This is close to the surface. So this part is moving faster, this part is moving slower, so that's why the wave will reflect. It will turn towards the surface. Okay, and then when it arrives at the surface, then at the surface the density suddenly drops. Okay, here we have larger density, here we have very small density. Then what will happen? There would be reflection. Then wave will reflect. Okay. So when it reflects, then again it will happen somewhere here. Then again from that on the wave it will reflect. So this way we can have several waves. They are trapped inside the sun, and when such waves they superimpose, uh, then they perturb the surface of the sun. Okay, so the surface oscillates up down. Okay, so in the previous picture that we have seen in this, so this is happening because of the millions of the sound waves. They are also called acoustic waves. Okay, so because of these acoustic waves, the surface is oscillating up and down. And if we can separate these waves, for example, here we have the green and blue. So you can see the green one is trapped close to the surface, and the blue one is going deep in the interior. On the other, in another way, you can say that the waves with shorter wavelength, okay, they are trapped close to the surface, and waves with longer wavelengths, they are trapped deep in the interior, right? Okay. So if we can separate these waves, different wavelength waves, then we can have information at a different depths. Okay. So this using this we can explore the interior of the sun, and this is called the heliosmology, studying the Earth's sun's interior using the oscillations is heliosmology. Okay, so how to model that? So that for that you can see, you can understand this way. So if you have a vessel here, okay, so in this we have the one dimensional wave, a standing wave. So one of the wave, let us say here it is the green one is propagating towards the left side and blue one towards the right hand side. Then the superposition of these two will produce the standing wave that you can see here, the the black one. Okay, so this is one dimensional case. The two dimensional case, for example, you can consider drum here, and if you hit the surface of the drum, so the drum surface will be oscillating in different modes. Okay, similarly, in case of sun, this is spherical object. Okay, so this is also oscillating in different modes, and these modes uh, we can model using the spherical harmonics. Okay, L is the harmonic degree and M is the azimuthal number, and theta and phi as function of latitude and longitude. So these oscillations we can model. For example, here you can see some of the illustration of the spherical harmonics. Okay. Uh, so the perturbation on the surface of the sun, we can find something like this using the equations that we have in the beginning, we have seen. So we can use those equations to model the perturbation on the surface of the sun, considering the spherical shape of the sun. So you find some constant here, then we have the spherical harmonics, and this is the time dependent term. In the spherical harmonics term here, again you see along with that we have n. So n is called the radial order. Okay, this can take values 0, plus minus 1, plus minus 2, plus minus 3. So all the positive values 0, 1, 2, 3, they are the acoustic modes. Okay, and the negative they are related with the internal gravity waves. Okay. So in the sun, the internal gravity waves, they are trapped in the inner part. Okay, so when they propagate towards the surface, their amplitude decay. So above the surface, their detection is very difficult, and there are some reports, but people do not believe in that. But if we can observe them, then clearly, then we can get a detail about the interior part. But the acoustic waves information, from the acoustic waves we can have only let us say the radiation zone, and some region to some depth to the radiation zone only, not deeper than that. So from the acoustic waves, and L is the harmonic degree. This can take value 0, 1, 2, 3, 4 like this, and this harmonic degree is related with the horizontal wave number. Okay, the kh, that is related with the wavelength of the wave 2 by lambda. So if L is large, then we will have a kh large, okay, and L is small, and also it depends upon the R. So R is the turning point where the wave is trapped. M is the azimuthal number. This can take a value between plus minus L. Okay. So these values, they're similar to the values that we have in quantum mechanics while studying the hydrogen atom. Okay. Here we have some examples of the spherical harmonics. In this leftmost column we have M0. Then here we have okay, so when M is 0, this is called the zonal modes, and when M and L, they are same, okay, then we have sectoral mode. For example, here you see L and M, they are same. L is 8, M is 8. Here we have L is 4 and M 4. Okay. So in this we have just the patterns, spherical harmonics, just it's vertical. Okay, and here we have horizontal. These are zonal type, and these are vertical, they are called sectoral type. Okay, and if you in between consider some values, means L and M, they are not same, then you will have the combination of the zonal and sectoral modes. In this, the red color represents the upward, can consider it's a downward motion towards the sun center, and blue part represents the motion towards us. Okay, and the red patches, they are the nodal points. Okay, so this way, using the spherical harmonics, here we have just a few of them, but if you consider different values of L and M, then you can model whatever you see on the surface of the sun, the oscillations. Here we have, okay, that we can model from that. So using the oscillations on the surface of the sun, we can have several properties of the sun. This is called the global heliosmology, when we consider the global oscillations of the sun, and we can find out the surface helium abundance, depth of the convection zone, tachocline. The tachocline is the region between the convection and the radiation zone. Okay, there is a layer there. We have uh, a differential rotation. Okay, too much differential rotation is there in the tachocline region. We can also find the temperature, density, sound speed, considering the global helios means global oscillations. This also helps us in understanding the nuclear reaction rates, opacity, chemical composition, and neutrino problem. Okay. You know the neutrino problem, that is a big problem in physics. So the from the global heliosmology, we had one of the proof about the temperature, inner core temperature, and then that leads to the understanding of the neutrino problem. But the global oscillations, global modes, they are insensitive to the local properties. If you want to study the local properties, so if you want to study local properties, you have to use the local oscillations. And in the local region, the waves, that they do not have the enough lifetime so that they can circumnavigate the sun. So their lifetime is less, very less. So they are trapped means in local region of the sun, and using those local oscillations, we can study the local properties. So here we have the the differential rotation, how in the interior the sun is rotating. Here we have 0 degree latitude, 15-degree latitude, 30-degree latitude, 45-degree, 60-degree latitude. Okay. Uh, and here we have the rotation rate. So you can see at different latitude the sun is going differentially, and around this region, you can say 0.6 0.67. At that point we have the tachocline region, and after that it's like a solid body rotation. Next, suppose you want to study the local interior of the sun. So what we can do, we can extract the oscillations in the local region. Okay, and we make a data cube. Here x-axis and y-axis, and here we have time. Okay, this is data cube, and then take the 3D Fourier transformation. Okay, when you take the 3D Fourier transformation, you will get trumpet-like structure. Here we have some slice of that only. So here we have kx, ky, the wave numbers, and omega, the temporal frequency 2 pi nu. Okay. And if you slice at a different frequency, you will get ring here. You can see this is for one position here. We have some ring structure, and if you increase the frequency, you can see how the ring is appearing. So this is from observations. So we took the observation here and then take the Fourier transformation, 3D Fourier transformation of it, and you get this kind of structure. So now the question is why we have this kind of structure, the ring shape structure. Okay, so that we can understand from the dispersion relation for acoustic wave. Actually, these patches that you are seeing here, they are representing the dispersion relation for the sound wave inside the sun. Okay, and the different rings, they corresponds to different radial order. Okay, so let us try to understand the rings. The dispersion relation for sound wave, we have omega square is equal to k square c square omega, and k, they are the temporal and spatial frequencies, they are related with that. Omega is 2 pi nu and k is 2 pi pi lambda. And k we can split into two parts, kx and ky. So now you see this omega square equal to kx square plus ky square into c square. C is constant. Okay, C is so. Then we have the variable kx, ky, and omega. C is the sound speed. Okay, that is constant for. So if you fix omega, you will have one circle. For example, here we have, and if you fix one of these, let us say fix ky. So here we have kx, k omega plot. So this would be a straight line like this. Okay, and if you rotate this omega equal to kc around the omega axis, so you will have a cone. Okay, and consider different frequencies. So you will have the trumpet shape like that you have seen here. Okay, so that way we can explain the trumpet shape and the ring structure in the power spectra. This spectra can gives us a lot of information. So for example, one information about uh, the flow. Suppose along the x-axis we have a flow. Okay, the flow is u. Okay, there is some plasma flowing in the x direction. Okay, so because of this, there would be a perturbation in the uh, in the in the frequency, and then we have omega minus. Initially we had that omega square equal to this, and then it will change omega minus kx u whole square equal to k square c square. And now based on this, if you try to plot, so you will get something like this. So initially we had something like this, then it will change the position. No, from here to here it will change the position. And also the ring, instead of we had the circle, now it would be in the elliptical shape. Why this is happening? This is happening because of this. This is the plasma flowing along the x-axis. So similarly, we can have the flow in any direction, not only in x and y. In direction we can have. So then, because of that, we will have the perturbation in the ring shape. Okay. So just by fitting these rings, we can find the flow along x and y directions. Okay. So this is just one ring here we have, and then here we have some artificial perturbation in the ring positions. Actually, this is obtained. Yeah, in this case, we see the sun is rotating differentially. So while constructing the data, if you do not remove the rotation, then there would be a the rotation effect, and because of the rotation, the rings will shift. So you can see the shift of the ring positions. So that will give us the flow, but this will be as function of this would be for different modes in radial order, harmonic degree. Okay, then that we have to use to convert into the actual flow that we have in the interior. Okay, so that we can understand from this equation. We can see this ui. This one can obtain from by fitting the ring that we have here. This And this can be expressed as, here we have KIR, UR, and UR is the actual velocity at the depth R. Epsilon I, this is the error in the UI fitting. And KI, this is called the kernel. For a given mode, we know the kernel means from the model, theoretical model, we can we can find out the kernel values. So UI is known to us, KIR, this is known to us, epsilon I is known to us. So UR is the unknown. Okay, this is called Fredholm inverse uh, a problem of first kind. This is Fredholm equation of the first kind. So this is a inverse problem. Okay, and this is ill-posed problem, because in this kind of equations, uh, if you this you can convert to the, just by considering the you can, using quadrature rule like that, you can convert this equation to summation, and then you can set up a set of linear equations. And in that you will see that if you do a small perturbation in the coefficient matrix, there would be large changes in the solution. So this is a kind of ill-posed problem. Okay, so then we there are some methods to solve this. Uh, so here I'm going to show you some result. I'm not going to discuss the detailed part about it, that the technical part, how to invert it. That is also very interesting. So suppose here we have, let us take one image of the sun. This is in 2003, October 2003, we had some active region on the surface of the sun. You can see some numbers. These numbers, they are called the nova number. Okay, some all the active regions, we give some number, and if you want to refer the active regions, so we call them using these numbers. Okay, so there are some big active region on the surface of the sun. I'm going to show the interior, in the interior of the sun, what is happening. Okay, so here we have the flow, horizontal flow on the surface of the sun, and you can see right hand side we have a bar that is going from the top to down as we go. I mean, this top is representing uh, the surface, and when it is going down, then it is representing the depth. Okay, x-axis here we have longitude, y-axis we have latitude. Okay, this is covering only plus minus 60 degree in the longitude and latitude, just like this small part only, because when you go towards the limb side, there would be a projection effect. What is the projection effect? You see the grid here, they are drawn at a distance of 10 degree. Okay, so 10 degree, you see this is 10 degree, this is 10 degree, total 90 degree we have here. Let us say in the vertical, this is the vertical meridian, central meridian, and here we have minus 90 degree, and right side we have plus 90 degree, and the latitude we have plus 90 degree and minus 90 degree. So the grids, they are at a spacing of 10 degree. So here we have 10 degree and 10 degree. Now every box, they are representing actually the same area, but you see here close to the limb, uh, we see the box's size is small. Okay, but actually they are representing the same area. Why this is happening? This is happening because of the projection effect. Okay, the sun is spherical in shape. Okay, so this part we are not seeing the actual, it is just the projection. So this big area is compressed in the smaller area. Okay, so just considering this a small region plus minus 60 degree, where we have a less projection effect. Then what we find, in the interior of the active region, the flow is twisted. You see some kind of twisted flow like this, and some quiet region area, the flow is like this. Okay, so this is the difference between the flow in the interior of active region and the quiet region. Okay, and along this the vertical line where we have this the active region, this active region 10486. So what we see, okay, what we are computing, we are going to compute the helicity, kinetic helicity. This is defined as the helicity, kinetic helicity is defined as the volume integral of the velocity, scalar product of the velocity and vorticity. Okay, so this part is this part, the kinetic helicity density, because we are not having the flow in the entire volume, so we can only find the integrand part. So this give us how the flow. See, omega is the curl of u. Okay, this is called vorticity. Omega is curl of u. So it means how the flow is twisted around. Okay, how the flow is twisted, that is going to give the u, square product of u and omega. So we find something like this. On the top you see x-axis, we have the latitude along this, or you can say you can have a vertical line here. Okay, so that is the x position here, and here we have the magnetic flux. So in the active region, there is a strong magnetic field. Okay, so we have larger values, and in the interior we see there is a twisted flow. Okay, you see the positive and negative, uh, the kinetic helicity is there, and in the quiet regions we do not find any significant this kind of flow. Okay, and this the twisted flow, one can try to understand the flare. What are the flares? You see here in this picture, the there is a eruption. This eruption, here we have the surface of the sun, and from the surface of the sun there is a eruption. You see, suddenly some energy is going up. Okay, some particles going up, and then uh, after that they are returning, some part is returning toward the surface because of the gravity. Strong gravity is there in the surface, in the sun, and some part will be going outward, so that will go in the heliosphere. So it is challenging to predict when uh, also it is interesting uh, whether we can predict this kind of activity in the sun. Means, why do solar flare occur? Okay. So what we have found, that in the interior of the active region we have this kind of flow. Okay. This kind of flow is there, and that flow twist the field lines. Okay, see the magnetic field lines, they are trapped in the interior. Okay, so the flow in the interior, that may twist the field lines. Okay, when there is a twist, so there is going to we are going to accumulate more and more energy in the field. Okay, and then after some time what will happen, this will break. Okay, and then we will have the flare. uh, so that is one possible explanation for this from the interior dynamics. Okay. Okay, so this way we have covered the interior part. Now about the solar atmosphere. uh, uh, the atmosphere above the solar surface we cannot see, because we are having intense radiation from the photosphere. But if there is a full eclipse, then we can see the atmosphere. We can see some colorful region, the chromosphere, that is called uh, the actually in the chromosphere region we have radiation, more radiation in the red color region, that is from the spectral line, the H alpha line. That's why we have the color region. So if you want to study the atmosphere, so you have to block the radiation. Here we have, let's say this is the sun, and from the sun we have the radiation outward. When the radiation from the sun uh, propagate outward, then it interacts with the atmosphere, its atmosphere, and when it enter in the earth atmosphere, so there also it interact with the earth atmospheric particles. Okay, so we can have this kind of a spectrum. So here the black line that you are seeing, this is the black body spectrum, and on the top of the earth atmosphere, if you observe, so you will find the yellow color. Okay. So this is almost matching with the black body curve, so one can consider the sun as a black body. But from the earth, when we observe, so there are some absorption. Okay, you can see here there are some absorption. So this absorption happen because of the atmospheric particles and the vapors. Here we have the H2O, a water vapor. So most of the radiation here we have in the visible region. Okay. It was Fraunhofer who observed some spectral lines in the solar atmosphere, and the spectral lines you can see A, B, C, D, E, F, G. Okay, the spectral lines. So some of these spectral lines, they are from the Earth atmosphere, and another from the solar atmosphere, and one can use these spectral lines to study the metallicity, the ions available in the solar atmosphere. In the atmosphere, the temperature, it's a million degree Kelvin. So the surface of the sun we have around 6,000 degree, and above the surface, after the surface, the temperature decreases. That is in the temperature minimum region, that is called the lower chromosphere, also it is called, and then it increases in the chromospheric region. Okay. And then again after that it increases suddenly, that is called transition region. Then we have the coronal temperature in million degree Kelvin. So here we have the profile, temperature profile like this, and in different regions, the x-axis is the height here from the surface of the sun, and y-axis is the temperature. So at different heights, you can see the formation of the different spectral lines. Okay, here we have the calcium, then nickel in the photosphere, G band we have. In the chromosphere we have H alpha and calcium spectral lines. In the transition region we have helium 2, and when you go to the corona you will have iron ions. Okay, so if you observe in these spectral lines, one can observe different layers of the sun. Okay, so this is one example of the solar eclipse, the eclipse of 1999. So the moon has covered the sun entirely. The photosphere has been covered. Then you can see some colorful here layers, some colorful features that belongs to the chromospheric emission, H alpha emission. And in the chromosphere we have some features. For example, filament we have. You can see here dark features like this. So this is just above the photosphere we are talking, in the H alpha. So then there are some here bright regions. You can see the plages, and you can see some structures above the surface. They are called the prominence. Actually, the prominence, then filaments, they are manifestations of the magnetic field in the solar atmosphere. Okay. This is the hydrogen spectral lines, and from this, here we have the ground state, then the high energy state, and we can have the Balmer lines here, Balmer Austin different series, and from this we can find the the wavelengths and emissions in the hydrogen, and that you can compare uh, with the with the spectral lines that you observe from the sun. Then you can find the wavelength associated with that. Now come to the corona. So uh, if you uh, if you block the radiation coming from the photosphere and also the chromosphere, then you can see the higher atmosphere of the sun, that is called the corona. Okay. In the corona, we have also different structures again. Okay. So they are these different structures. They are because of the magnetic field in the corona. And there we have this flare. So why the flares we have? The flare we have because of the reconnection of the magnetic fields. Okay, so here right hand side there is one animation how the reconnection is happening. Okay, you can see at this point. So suppose we have some field, magnetic field like this. Okay, and there is inflow. So when there is an inflow, then this part and this part it will join. Okay, and the upper part it will be disconnected, and the lower part will be like this, is combining like this. Here we have. Okay. So that is the reconnection happening. So once there is a reconnection, you will have the ejection of the energy that comes out from the sun. So this way we explain the flares using the magnetic reconnections. Then in the solar atmosphere we have the ejection of some masses, some particles, that is called coronal mass ejections. You can see uh, there is some blob of the materials coming out. Okay. That is called the coronal mass ejections. And here we have the measurement of the solar wind. Okay. This is from some theoretical model, and here we have the observations of the solar wind. Okay. So the wind speed in this region, you see how it is changing. The wind is around 400. Wind speed is around 400 kilometers per second. Okay. So it is coming from the outer atmosphere of the sun, that is the solar corona, and that can the ejections can affect the sun, affect our Earth like this. In this animation, you can see there is a flare happening. Then from that there is some ejection of the particles, energetic particles, and when they arrive to the Earth, then there is a reconfiguration of the Earth's magnetic field, and some of the plasma particles, they are entering in the polar region in the north and south part of the Earth. Okay, and when those particles they interact with the Earth's atmospheric particles, then we have the beautiful feature, that is the aurora borealis. Okay, so this is the summary of my talk. So the sun is the nearest star to us, which is the ultimate source of the energy. And if we one can study the detail about the sun because it is near to us, and we can study about the interior, atmosphere, surface, and uh, once we know more about the sun, then we can know detail about the other stars which we cannot observe we cannot, especially means with their surface detail we cannot observe because they are so far from us. And by studying the interior of the sun, their energetic activities, we can have a prediction about uh, when this some solar eruption is going to happen. And once we have the successful model, we can give prior information to astronauts, the space. Also, we can save our space stations, and and other assets we can get saved. So that's all. Here we have some observatory that we have in India. For example, Udaipur Solar Observatory. And uh, this is part of the Physical Research Laboratory, Ahmedabad. Okay, this was founded in 1976 by Arvind Bhatnagar. There we have a new telescope. It's called MUST, Multi-Application Solar Telescope. Its diameter is 50 centimeter. Uh, Another observatory, here we have the Kodaikanal Solar Observatory. This is part of the Indian Institute of Astrophysics. It was founded in 1899. It's the one of the oldest observatory in India. And it's the first. The director was Everser, John Everser. So he has a lot of contribution in the solar physics. The IIA, Indian Institute of Astrophysics, they are planning to have a telescope, a larger telescope. It's called a National Large Solar Telescope uh, in Henley. Okay. Its diameter would be 200 centimeters. So if the diameter is big, then we can get a better spatial resolution. I had opportunity to observe the sun from Big Bear. So from there I took this picture. So this telescope is the National Solar Telescope. It is in Big Bear. The diameter is 1.6 meter. There are some other planned, for example, Chinese giant solar telescope. They have planned their the purchase size 5 meter. Okay. So that would be really very big telescope. Uh, so there are some constraints for the observations from the Earth, because the these observations, they are contaminated by the Earth atmosphere. Another thing is that there is a gap in the observations because of the night. Okay? If you want to study the interior of the sun, so we should have continuous observations. Uh, so if from the Earth surface, and from one place we cannot observe 24 hour. So there are the possible ways are: one, we can establish telescope around the globe. Okay. uh, when at one station sun is setting, the other station it would be rising. Okay. Or if you have several telescopes, then it will never set. Okay. We can have continuous observation of the sun. Or you can go to the polar region, where we have 6 month days observations. The third option is that we can send our telescope in the space, so we can have the continuous observation of the sun. So this is uh, the Global Oscillation Network group. It's called GONG. So there are 6 stations around the globe. Okay, one station here, and one of this is in Udaipur. Okay, so you can see this. So they observe the sun continuously to study the interior of the sun. Okay. Uh, and this, and from the space we can observe. Okay, some space-based observatories are Parker's Solar Probe, IRIS Interface Region Imaging spectroscopy, and Solar Dynamics Observatory, Hinode, Trace, Soho. Okay, so these are different space-based observatories. Uh, so they provide better data. So there is no atmospheric contamination, but there is constant with the space-based observatories also. For example, one thing is that it is very expensive to set up a telescope in the space, and it is also difficult to repair and upgrade if you have set up a telescope in the space. Okay, so with this I want to stop here. I think I have taken a lot of time.
Thank you, sir. We should have some discussions, I think, since all of you are listening to the talk for quite long. One important part of this FDP program is discussions and doubt clearance with the speaker. So you can unmute and ask if you have any type of doubts, or if you want anything to be explained further. So all these things are possible. Uh, any doubts? Okay, so if we don't have any doubt, then I think we can stop this discussions at
Sir,
present.
I have one doubt, sir.
Yeah.
Sir, can you put? Is it possible to put the content slide of this, sir, so that it will be available? You will be posting it, madam, sir. Am I right? It will be the group, sir. Table of contents of this slide, sir.
We will request the speaker whether he
Okay,
can
sir. Thank
share
you.
some
Thank you, sir.
slides. Yeah.
Thank you so much, sir. Okay, sir. Okay.